Hey guys, welcome back to my AP Chemistry video series. In today's video, we're going to be talking more on ionic compounds, specifically on how to name the ionic compounds and how they behave. First off, let's start off with talking about polyatomic ions. By definition, a polyatomic ion is an ion with more than one atom. For example, chloride is not a polyatomic ion because the only atom present is chlorine. Now, it doesn't mean that there's only one type of atom. There can be one type of atom and still count as a polyatomic ion. Azide is one of them. It only contains one type of atom, nitrogen, but it's still considered a polyatomic ion because there are three atoms, not one. Now, azide is one of the rarer ions that you don't have to memorize, but the common ones you have to know. Here I have two charts with the common polyatomic ions. Take a look at the first chart. So the first ion is NH4+, the ammonium ion. The ammonium ion is the conjugate acid of a very common household base, ammonia. And by far, it's the only cation that made its way into the common polyatomic ion chart. It has no alternative names, and it has a charge of +1. The second one is, as you can see, carbonate, with the formula CO3 2-. Carbonates are bases, and again, these guys you will encounter a lot when you're practicing in the lab. And as you go on, you'll notice that I have 4 ions that are hypochlorite, chloride, chlorate, and perchlorate. Now, why do they call it this? Well, let's start at chlorate first. At chlorate, the oxidation state of chlorine, if you watch the oxidation state video, you'll know that the oxidation state of chlorine here is that after a bit of math, +5. Now, if the oxidation state increases, we need to make a per prefix. Because the perchlorate ion features chlorine in the 7+ oxidation state, we're supposed to call it perchlorate. Now, what if the oxidation state goes down as you do it? Well, chlorite is just the case. Chlorite has a +3 chlorine, so the ate suffix changes to an ite suffix. See how it's going here? And finally, if the oxidation state goes really low, like say in hypochlorite where chlorine is just +1, then the hypo prefix is added to the ion's name. So it makes hypochlorite. Now if you go down to the negative oxidation states of chlorine, well actually -1 only, you're only going to have to add the suffix "ide." We're going to talk about naming monoatomic ions a little later. Now the same example here, nitrite is called that because nitrogen 3+ and nitrate is there because it's nitrogen 5. 5 is more than 3, and therefore this ion deserves nitrate and this guy only gets nitrite. Let's look at some more common polyatomic ions. So if you go down like this, you hit bisulfite. Bisulfite is also known as hydrogen sulfite, just like bicarbonate over here is also known as hydrogen carbonate. This is because if you add one hydrogen ion, more like an acidic hydrogen ion, you get this ion. So if you add one H+ sulfite, you get bisulfite. So it only makes sense to call it hydrogen sulfite. Sometimes they'll call it the acidic form, but that's really rare and you don't really have to care about it. The same thing goes for bisulfate. You can also call it hydrogen sulfate. The next ones are permanganate, chromate, dichromate, rarely called bichromate, disulfate, rarely called hyposulfite, followed by phosphate, hydrogen phosphate, and dihydrogen phosphate. What makes these two ions different from each other is that hydrogen phosphate only has 1 H+, while dihydrogen phosphate has 2. So now you just need to take a look at these charts to memorize it. So I'll give you a few seconds to look at this. And I'll also give you a few seconds to look at this. Feel free to take screenshots while you're at it. Okay, so I think that's enough time to take a screenshot. So now let's look at ionic formulas, or more like the name of ionic compounds. When you make a name of an ionic compound, you first call the cation's name and then the anion's name. For here, I have ammonium ion, which is our cation, and chloride as our anion. So the ionic compound that forms from these will be logically called ammonium chloride. Now what if the cation has more than one possible oxidation states for the same element? Like chromium here. Chromium 3 is very common, but chromium 2 ions also exist. Well, then we use something called the stock system. The idea is that you first name the element's name, for our case chromium, and then you put the oxidation state inside parentheses in the form of Roman numerals. Because the oxidation state is apparently 3, we put 1, 2, and 3 I's representing 3. There are some tutorials on Roman numerals here and there, so you might want to know that before you move on to the stock system. Okay, so now we get our anion, nitrate, and if you mash them together, you get chromium 3 nitrate. Now when you put an ionic compound together, the total charge must always equal 0, otherwise it's still going to be an ion. So here, it's only logical to put 3 nitrate ions because nitrate's charge is only 1 minus. Let's move on to some more info. An ionic compound, also known as a salt, can be split up into a metal cation and non-metal anion. What's funny though is that in the metal cation, ammonium is considered a metal, although you can never find the metal here. Nitrogen and hydrogen are both non-metals, but they still count it as a metal. We also have non-metal anions. We also include polyatomic ions, which another thing that makes it funnier is that if you go back to our polyatomic ions chart, permanganate, chromate, and dichromate contain metals. Permanganate is manganese, and chromate and dichromate contain chromium. Except here is considered a non-metal, since it's an anion. And I find that kind of weird. And as I already mentioned, the name is split into the cation and then the anion. For instance, calcium, cation, and chloride, anion. Let's look at some more detail on how to name our ionic compounds. If the cation, or more like the element of the cation, only has one possible oxidation state, then we just put the name of the metal followed by the name of the anion. For instance, sodium chloride is called like that because sodium only has one oxidation state, sodium 1 plus. So it's only logical to put sodium 1 plus, or more like sodium, and then the name of the anion, chloride, and make sodium chloride. But what if the metal of the cation has multiple charges, like say tin? Well, as mentioned before, let's use the stock system. If we use tin 2 chloride, for instance, the tin, Sn, and 2, here, because it's 2, we put 2 plus, and of course we put our anion name, chloride. Now because tin's oxidation state here is 2 plus, we put 2 chlorines. Now how does this differentiate from tin's higher chloride, tin tetrachloride or tin 4 chloride? Well, as you can see, the Roman numeral in the two of them are different, right? This one's 2, this one's 4. So you can help us clearly see what oxidation of tin is present and the chemical formula of these chemical compounds. Now let's look at anion names. If the anion name is polyatomic, then you can go back to our polyatomic ion chart and pull up our names, or you can just put in these prefixes by using some logic. If an anion is monoatomic, then we put the name of the element and then put an "ide" suffix. For the case of bromine, right here, bromine, which is Br, will form Br minus, right? Since it's a halogen and it'll gain 1 electron to get the noble gas configuration. Check out our AP Chemistry 5 video to know some extra information about that. Anyway, now Br minus is an ion, not an element. So we cross off I and E, ene, and put IDE, ide. This is true for any halogen element. Fluorine becomes fluoride, chlorine becomes chloride, bromine becomes bromide, and iodine becomes iodide. Well, let's look at some other non-halogen elements. For instance, sulfur right here. Sulfur is logically S, and 2 minus is the charge it gets. Except here, the last three letters is FUR, fur. Well, we're still going to get rid of it, except this F is going to be spared. The UR goes away, and the ion's name becomes sulfide. So you can know that the sulfur is the anion present for this salt. Now, what if you don't know the charge of the cation, but only the charge of the anion? Well, we can use a knowledge of oxidation states. So first, let's split up our ionic compound. This is lead iodide, except we don't know the oxidation state of lead yet. Well, if you split it apart, you get lead X plus, since you don't know the oxidation state, and 2 iodide ions, right? Because it's a subscript of 2. Well, because 2 multiplied by this 1 minus becomes negative 2, and because we're supposed to make the overall charge equal to 0, logically the lead's charge is 2 plus. But what if it's something a little more complex, let's say? For instance, let's say we have chromium sulfate. We don't know the oxidation state of chromium. Again, we have to split up our molecule. So 2 chromium X plus and 3 sulfate 2 minus. And you can see 3 times negative 2 is logically negative 6 from your 6th grade math class, or maybe 7th grade. And because negative 6 plus something is equal to 0, X is going to have to equal positive 6, right? Except now, you're going to have to distribute the plus 6 charge across these 2 chromium atoms. So you divide the 6 by the 2, and obviously you get 3. So the oxidation state of chromium is 3. So you can already see how to figure out oxidation states of the cation, even without knowing what it is. Just because you know in charge of the anion and our basic knowledge of oxidation states. Let's look at how our ions behave in solution. If we add a salt to some water, let's say distilled water, then the salt will decompose into the cations and the anions. For instance, for my example of sodium sulfide, it will break down into sodium ions and sulfide ions. Let's look at another example. For nickel 2 chloride here, nickel will become nickel 2 plus, and the chloride will dissolve to form chloride ions. Except because we have a subscript of 2 here, it will now become the coefficient of chloride. So there will be 2 chloride ions in solution for every 1 nickel 2 plus ion. What if our ion is polyatomic? For instance, here copper 2 nitrate. Well then, when we dissolve it in water, the copper with the subscript of 1 will get a coefficient of 1. Of course, both of them are ignored since we assume it's 1. And because nitrate is in parentheses, the subscript outside of the parentheses will become the new coefficient. So we have 2 nitrates. Here are some basic solubility rules. Let me just add number 8. So here are some basic solubility rules. Now there's 8 of them, and here are some simple ones. Now you'll learn more rules and more exceptions as you get to higher levels, but right now we don't need to care about it. So we just have 8 simple rules you need to follow. The first one is that all nitrate salts are soluble. There are exceptions, but ignore them for now, since they don't really show up until the higher levels of chemistry. 2. Almost all lithium, sodium, potassium, rubidium, and cesium salts, or basically just any alkali metal salt, is soluble.
Even if the counter ion, in other words the anion, is not soluble for most other ions, if an alkali metal ion is present, it will be soluble. Number 3, all ammonium salts are soluble as well. Again, there are exceptions, but we'll ignore them. Number 4, all acetates are soluble as well. In case you're wondering what acetate is, in case you haven't watched our videos, acetate is the conjugate base of acetic acid, which is the compound contained in vinegar. Number 5, all carbonates and phosphates are insoluble in water. The only exceptions are, of course, ammonium and the alkali metals. Number 6, all hydroxide salts are insoluble. Again, alkali metals are exceptions. And for number 6, barium also becomes an exception as well. Number 7, all chromates are insoluble. That is, again, except for all alkali metal salts. And number 8, and the last one, all sulfides and oxides are insoluble, except for, again, the alkali metals. Some sulfides, other than alkali metal ones like barium, strontium, calcium, or magnesium sulfide are soluble, and certain oxides will also react with water. But for now, these are just the rules that you have to follow. It's a good idea that you memorize all of them. Let me give you a moment to memorize the chart. Okay, so now let's look at the double displacement reactions. It's just how the ions behave and interact in solution. So let's say, as a curious chemist, I mix the solution of barium nitrate and sodium sulfate. Now, I'm gonna get something, right? There's gotta be a reaction. But what forms? Now, first we need to identify the ions that form when these salts dissolve into solution. Logically, barium nitrate dissociates into barium and nitrate ions. And of course, sodium sulfate becomes sodium and sulfate. Now, there are 10 possible routes using two ions. Now, these first four, sodium, sodium, barium, barium, sulfate, sulfate, and nitrate, nitrate pairs are impossible because you can't form a compound with two identical ions. Because as you all know by now, cations repel from other cations and anions do the same thing. So you can't have a compound that's either only composed of cations or only composed of anions. You need both. So logically, these combinations, sulfate nitrate and sodium barium combinations, are impossible as well because you're using two anions or two cations to make a compound. It won't work. Now if we look at the reaction of sodium ions and sulfate ions and barium ions and nitrate ions, they will react to form sodium sulfate and barium nitrate, except the fact that they're already present as our reactants. So I don't think that's going to happen. And the last two, which is barium ions reacting with sulfate ions and sodium ions binding to nitrate, forming barium sulfate and sodium nitrate, are possibilities. They're not necessarily true, but they might be true. Number 3, we also need to use our possibilities that we got to obtain a chemical equation. So, barium nitrate, let me write them down, barium nitrate and sodium sulfate form barium sulfate. Makes sense, right? The anions switch places, and sodium nitrate. Now because the subscript of sodium and nitrate is 2, it's only logical to make the coefficient of sodium nitrate 2. So that's how you figure out what is present in a double displacement reaction. And in our entire video, we talked about how to name ions, how to identify the charge of ions, and how to identify how ions behave. Thanks for watching, and see you in our next AP Chemistry videos. Bye!